the mesh software to find the software bugs. And of course, the developers never write software to defeat his debugger. So I think that people just happen to use the debugger to analyze malware because they know how debugger works, and the debugger can be used to change the execution of the malware. But the debugger is never built to analyze the malware, and that's why you have so many problems, and all of them cannot be fixed. Okay, on the second part, we introduce the Virt-ICE problem, the architecture, design, implementation, and the main features. So here's our idea to solve all of those problems. So because the malware can detect the debugger, so we try to solve that by making the debugger invisible to the malware. So malware cannot see the debugger anymore. So we solve that. Second one, because the malware can detect, can attack the debugger, so we try to put the debugger out of the reach of the malware by running the debugger in another protection domain, so malware cannot attack it anymore. So we solve two problems. And here's our approach for Virt-ICE. We run the malware inside the virtual machine. And this requirement actually doesn't introduce any problem because already people already use virtual machine to analyze malware for a long time. So this one is not the burden for malware analysts. And running malware inside virtual machine, we use fine-grained instrumentation technique. We instrument guess virtual machine to intercept guess execution at any time and anywhere we want to. And after that, we put the debugger specifically inside the hypervisor or emulator layer of the virtual machine. And the debugger staying here, so it is out of the reach of the malware running inside the cache. The cache cannot attack the debugger running at the lower layer. So here's the architecture. So you can see that we run the malware inside the guest VM, and we run the core component of the Virt-ICE in the hypervisor layer. So there's some other benefits for Virt-ICE. Because we run the debugger inside the hypervisor layer, so we have the whole system view, so whole system analysis is possible. And especially ring zero code, for example, rootkit, debugging is better than anything else available out there because you can debug anywhere, anytime. Normal debugger can also be used to debug the kernel, but there's some restriction. For example, there's some place you cannot debug, and there's some restriction that you cannot overcome. So this approach helps us to fix all the unfixable problems we introduced before. So you can see that Virt-ICE is invisible to the malware. Why? Because normal debugger uses system service for debugging, right? But Virt-ICE doesn't use a system service because we use instrumentation from the bottom layer, and we can even have better technique to debugging. The second problem, the normal debugger modifies malware process. Virt-ICE doesn't do anything like that because instrumentation at the bottom layer never modifies the malware process. We don't need to modify malware process. We don't need to inject software breakpoint into malware process. And finally, the normal debugger is staying in the same domain with the malware, but Virt-ICE stays outside in the lower layer. And we never use any agent inside the cache. We don't need any help from the cache. We need zero help. So we stay completely outside. So we are completely invisible. And finally, Virt-ICE cannot be attacked by malware because it stays at the lower layer. And malware cannot attack to the outside. That's guaranteed by the virtual machine design. Okay, so here are some requirements to build when you build Virt-ICE. First, you need to understand the cache context from outside. You run debugger outside, but you need to understand the cache context from outside without any support from the OS inside. And after that, you need to instrument the guest virtual machine execution. So using the instrumentation, you can set breakpoint, watchpoint any way you want to. And after that, from outside, you need to access to the virtual machine context. You need to read and write to virtual machine memory. You need to read and write to CPU context of the guest. And finally, Virt-ICE also need to manage the virtual machine. You need to pause virtual machine, resume virtual machine when you want to. And those are all the requirements you need to satisfy when you build Virt-ICE. Okay, so on the first problem, how to understand guest context from outside. So note that we must do everything from outside without any support of the guest virtual machine. And this is called virtual machine introspection problem. And on this part, we use the work done from last year. So we can see our presentation at several conferences last year. And we use a framework named EaglEye. EaglEye framework help us to extract OS semantics object from the memory of the virtual machine. And now we support Windows OS. Okay, so on the EaglEye need to access to the guest memory and CPU context from the host, from the lower layer. And to access to the guest memory and CPU context, we need the help from the Kubota framework, which we introduce later. After that, after we can get access to the memory and CPU context, we need to get the OS objects from the memory of the guest virtual machine. And because we are focused on malware, so we focus on getting the object that can be exploited by malware, like network port, connection processes, DNN, registry, kernel module, and so on. Here's a full architecture of EaglEye framework. You can see that EaglEye framework is split in multiple layers. And each layer, the bottom layer provides a service to the higher layer. So to build EaglEye, you have many challenges. There are two challenges. There are just one challenge. EaglEye need to get a semantic object from the memory of the guest virtual machine. And this job requires excellent understanding on the OS internals. So to get OS object from the memory, we have two things to do. First, we need to locate the OS object. We need to, first of all, you want to get all the processes running inside the guest from the memory. You need to locate all the process in the memory. And so on, if you want to get a list of all the kernel module in the memory, you need to access to those objects of the kernel module, and so on. So on this part, actually, we don't invent anything new. How to locate those objects already presented by many research in the community. You can search many people on how to locate those objects in the memory. Okay, so after you locate those objects, you need to get information from inside each object. First of all, you can locate a process object somewhere in the memory. But that's not enough. After that, you need to extract the malware field from this structure in the memory. So first of all, if you want to know the create time of this process, you need to know that the create time field of this structure stays at the offset 70. And this field has a size 8. Right? You need to know where it stays in the structure, in the size of that. And so that means you must understand the object structure. But the problem is that those structure, the format of those structure can be changed between Windows version and even between service pack. It's not fixed. First of all, Microsoft can insert a new field in the next version of Windows anywhere, or they can exchange the those two fields anytime. So the offset is not fixed, and sometimes the size of those fields are not fixed either. So how to solve this problem? So there are many work also want to extract the object from the memory like that, and the solution is that they hard code on the popular objects and offset and size of popular field in the program. Everybody does that, but that's not good enough for us, because this solution you can only extract information, extract limited information. Just limited to the object you specify your source code. It's limited to the offset you specify. And for those not specified, you cannot extract out. So I have a dream. I want to be able to query structure on the object in Windows OS with all the field inside each object. And I want to do that with all the OS, not only Windows. And I want to do that on demand at runtime, not at compile time, with all kind of objects. And I want to answer many questions. First of all, I want to know the size of these objects. I want to know the offset of this member field inside this object. And we solve this problem with one framework named LibDI. And LibDI satisfies all the requests and make your dream come true. It's another framework. And LibDI rely on the public information on OS object. It doesn't depend on OS actually. And this framework supports Linux and Windows now. And we extract information by relying on debugging format. And we extract them from the debugging format. So for Windows, we have no contact with Microsoft, so we need to rely on the public information. And one of them is ReactOS. ReactOS is open source OS, which try to emulate Windows. So the idea is that you can run Windows software without needing to buy Windows OS. So you can run Windows software on ReactOS. And ReactOS is free and open source. Support from Windows 2003 and up. Windows XP and prior version are not supported. So here's simple ReactOS code. Of course, this one is only patched by me because the original ReactOS information they don't support Windows XP. So you can see that the structure is defined based on the Windows version. If Windows is before Windows 2003, it has that field. If Windows is after Windows Vista, it has those fields. So we build the Windows object. We compile Windows. We compile ReactOS file header to prototype with debugging information, and after that we extract information from the debugging file format. So first of all, here's how I build the object for Windows XP. We use Z++, build a dummy file which only include some object file I'm interested to, and I define that I define the Windows XP macro, and after that I output one object file for Windows XP. And the object file Windows XP service package.o include all the information about all the object file, about all the structure of Windows. So there are some problems anyway. ReactOS only support Windows 2003 and up, as I said. So I need to patch ReactOS header to support Windows XP. And I rely on the information from Windows debugging simulator, and patch size quite small. I also need to fix ReactOS prototype to support other Windows OS like Windows Vista or Windows 7. So here's a simple API for LibDI. You can see that there are three functions. You can get the structure size with the top function. Just give the structure name. Second function, give you the member size of the member inside structure. Just give it the structure name and structure member name. The last function, give you the offset of that member. Give it the shape information, structure